Good day, everybody. Today I want to look at the concept of limits and how that relates to the derivative of a function at a point. So the derivative at a point. So here we have a graph and there's a hole in the graph. Why is there a hole in the graph? And so we sometimes put something like that and we want us to find the limit. But so where does something like this come from? Well, it really comes from a nicer function. So here is a fourth degree polynomial, which isn't maybe too nice. I've got a simpler one for the next example, but I decided to start somewhat complicated here. So we've got this fourth degree polynomial. I'm going to fix a point, namely x equals 1, y equals 2. So I'm going to fix that point and find the slope of what we call secant lines connecting other points on this graph to that point at 1, 2. So here's the function. I've got the point 1, 2, which will be fixed, call that point P. And then I've got other points on the curve, and I'll call those maybe points Q, but for any x, the y value would be given by the rule of the function. So I just rewrote the rule there. And what we want to do is connect a line from P to Q, and that'll be the slope of the secant line. But then we want to let Q get closer and closer to P. And so then we can always find the slope of the line, except if Q equals P, then the 2 points are the same. You can't find the slope of the line through those 2 points. And that's where the hole in the graph comes in. So this will demonstrate that. I've got P fixed here, and Q, right now Q's off the picture there, but Q's at x equals -1, and then that's too high up. But so I'll start to move it in a little bit here. It'll come in quickly. I wanted it symmetric so that I definitely go through the point Q equals 1. So right now Q is at -0.326, and then of course it's on the y value, so you can find the slope of that line. I mean, it's really far away, so but we get closer and closer, and as we get closer, the slope of the secant line settles down to a nice constant slope. And then if Q is also at 1, so both P and Q are now the same point. They're both at 1, 2. Well, I can't find the slope of that line, so that's why there's that hole in the graph. And then if Q is bigger, then these are the slopes. So what will be the slope of the line connecting P and Q? Well, it's just change in y over change in x. So the change in y is this polynomial, this fourth degree polynomial, -2 divided by the change in x, so x minus 1. And that's what I have graphed here. The 2's actually canceled, so let me see if I can put it there. I actually have the fourth degree polynomial -2 divided by x minus 1, but in the output the 2's canceled, so the output just showed this. And so this gives me the slope of the secant line. So let me go back to my fourth degree polynomial, my P and Q, which right now is x equals 0. So that's what we see here. And then the slope of this blue line, which is the secant lines, given by the y value on this curve right here. So at 0, 2, the slope is 0, because this is the point 1, 2, this is the point 0, 2. So the slope of the line is 2 minus 2 divided by 1 minus 0, so 0 over 1 is 0. And then as I change Q, the slope's getting steeper and steeper. It gets biggest right around there for the secant line. And then I'm getting closer and closer to the point 1, and then whoops, it disappears. If I get it exactly, there we go. Whoops, missed it again. And then once I go Q is not 1, then you can find the slope again. And so the slope of this blue line is given by the y value on this curve. And of course, it's sort of undefined at 1, but there is a limit, and it's kind of easy to see that the limit is right there at 1, so the slope should be 1. So here it is again. Now I have the secant line dashed, and the tangent line I have drawn in, and we'll see how we get closer to it as I get as q approaches 1. You can see that down here. As q approaches 1, those secant lines are approaching the tangent line, and then of course it disappears at the instant. But that's what the slope should be. So the slope of the tangent to this 4th degree polynomial should have slope 1. It's at the point x equals 1, y equals 2. Okay. So the slope of the secant, the limit converges to something, but technically, if you just look at the change in y over the change in x at x equals 1, well, this will be 2, so it'll be 2 minus 2 divided by 1 minus 1, so that's undefined, so there's a hole in the graph. But it does have a limit, and you can find it numerically. You can even find it algebraically. There's a nice known rule that is known. If you plug a number into a polynomial and you get 0, then that number is a root of the polynomial. So the polynomial must factor as x minus the root times a new polynomial of degree 1 smaller than the original polynomial. In other words, so here's my polynomial. It's kind of this part and then minus 2. So if I plug 1 into here, I get 2, and then I subtract 2. So either way, I'm getting 0. So p of 1 gives me 0. I mean, obviously these 2's canceled. So the polynomial factor is x minus the root, so x minus 1 times a new polynomial. I'm not showing the work here. You can use long division to get it. So I'm getting a new polynomial, and now if I plug 1 into this function, then I can compute the limit. If I plug 1 into this, I'll get 1 minus 4 plus 4, and that'll be 1. Pictorially, so there's the slope of the secant line given by this, which is, the minus 2, plus 2, minus 2. But the simplified polynomial looks like this. It's the exact same graph, except now there's no hole at 1, 1. Right, and again, this is the slope of the secant line. So if I put them one on top of the other, they're the same graph except at 1. So technically, as mathematicians, we say this expression is different than this expression. They're actually identical for every value of x except at x equals 1. This one is defined, it's 1, and the other one is undefined. So that's the only difference. But technically there is a difference, so they're technically two different expressions. But when you're finding a limit, what happens at the x value doesn't matter. So they both have the same limit as x goes to 1. So if you can do the algebra, you can plug 1 into the simplified expression and figure out what the limit is. I guess one more look at the secants getting close to the tangent. So we can get it there. They're at 1. Looks like that. Okay. There is a second way to get the slope, and that's, so then there's the 4th degree polynomial. I've got P and Q, but rather than put Q in terms of X, f of X, since I fixed P at 1, 2, Q is just some distance away from P. We're going to say it's H away from P in the X value. So if Q is H away from P, then it's at 1 plus H. And H could be negative, so it could be on the left. And then the Y value is you just plug 1 plus H into the rule of the function. And everything's the same then. We're just looking at H values instead of X values. So if I'm at, well, I'll go to 1. So if I'm at H equals 1, I'm at X equals 2 because it's 1 plus H gives me the Q value. Or if H is negative, around 0.5, get a little closer. If H is negative 0.5, then Q is at positive 0.5 because it's 1 plus H. So everything else is the same. It'll have a limit as H goes to 0 now. And so instead of X going to 1, it's H goes to 0. But again, it's undefined at H equals 0. If I look at the expression, this is f of 1 plus H divided by H. And if H is 0, it's going to be 0 over 0. Yeah, I should have said it's f of 1 plus H minus f of 1. You can even see that here. So f of 1 plus H minus f of 1. F of 1 was 2, so I just put the minus 2 there. So f of 1 plus H minus 2. So if H is 0, I have f of 1, which is 2, minus 2 divided by 0. I have 0 over 0, which is undefined. But it does have a limit. It's 1, which is the slope of the tangent line. One more thing for advanced work. Given any function, and rather than find the derivative at a point, you can just find the general derivative function, and then you can plug in your point after the fact. So if I want the derivative function, I call it df, f prime df. So there's my original function. This would be the f prime. And if I plug 1 into this function, I'll get 1, which tells me the slope of the tangent is 1. All right, let's do the work here. I've got, if you plug 1 in, then this would be 4, and I got minus 4, so they cancel. And then I've got 16 minus 15, so that'll be 1. So the derivative is 1. But I can also now get the slope of the tangent at every x value super quick. So we don't have to do all the hard work before. And then now here's the graph of every tangent line as I move from left to right. So for different x values, rather than secant lines, I'll just put the actual tangent line. There it is at 1. So these are all the tangent lines for all those different x's. And it's not too hard to find this derivative function. You can do it with a limit definition. Gradually we get to rules where we don't have to do the limit definition anymore. That's what students always want to jump to. Once they learn it, they're like, why do we have to be tortured with limit definitions when there's this much easier way to go from the function to the derivative function, and then I can get the value of the derivative at any point nice and quickly. Well, I mean, we want you to conceptually understand the derivative, so we make you do all this conceptual work. So the first example was a tough one. Let me make an easier one now. X squared. And again, I'm going to look at x equals 1. Now the y value is going to be 1. So before the x value was at 1, 2, slope was 1. Now my point on the curve is 1, 1. So it looks like that. So here's P, here's Q. Again, Q could be to the left of P or to the right as I graphed it. But I fix this point 1, 1 on the curve. And then for Q, It can be anywhere else, but once the x value is known, to be on the curve, the y value has to be the x value squared. So it's the point x squared. And x squared minus 1 divided by x minus 1 looks like this. So again, at x equals 1, I have 1 minus 1 over 1 minus 1, 0 over 0. So there's a hole in this graph of the secant if I do change in y over the change in x. I'm looking at x value, so I start at x equals negative 1, let x approach positive 1, and draw all the secants. Well, if q is at 1, 1, just like p, you can't draw a secant line. So it's don't have one there, but there is a limit. And again, just like before, p of x is x squared minus 1. P of 1 is 0, so that means you can factor x minus 1 out from it. And this one's easier to do. You get x plus 1. So p of x over x minus 1 is now just x plus 1. So in other words, when you get 0 over 0 with polynomials, then you can always do some algebra to simplify, and then you're just going to get a nice expression that you can actually then plug in the trouble point. Right? So if I try to plug 1 into here, I get 1 minus 1 over 1 minus 1, which is 0 over 0. It's indeterminate, undefined. But if you do the algebra to simplify, I now have x plus 1. And now I can let x go to 1, it'll be 2. So these two expressions, this difference quotient and x plus 1, are different. They're the same for every value of x, except that x equals 1. So they're not much different. For every value of x, they're the same, except that x equals 1. This one's undefined, and this one is defined. So they're going to have the same limit, because what happens at the x value doesn't affect the limit. So again, there's x squared minus 1 over x minus 1. Then simplifying, I just get x plus 1. It's the same graph. If I put them one on top of the other, whoops, not a good view there. There we go, one on top of the other, that hole gets filled in. So they're the same graph, except one has a hole and this one doesn't. So again, what I'm looking at is the secant line in blue, and the slope is given here in red. So at negative 1, if I'm on the curve, I'm at negative 1, 1. So here I'm at positive 1, 1, negative 1, 1. The slope of the line has slope 0. Change in y over change in x is 0 over 2. And there's the value of the slope. It's at y equals 0. But as I move along the curve, so there's the q, the slope of this line is given by this y value here. So, which is actually going to be 1 plus x. If I get to 0, then the slope would be 1. So this has slope 1. And then I'm approaching slope 2. Which you can see right there. The slope wants to be 2. But technically it's undefined. So here it is with the tangent line. That tangent line has slope 2, and that's what the secant line slopes are approaching. Again, a lot of graphs to look at here, but this is the slope, so it wants to be 2, but otherwise the slope is given by whatever the y value is here for the same x value. So did I go to 0 here? So at 0, I'm going from 0, 0 to 1, 1. That has slope 1, and that's given by right here, right? The slope is right there. And if I go all the way to 2, this is the point 2, 4 on the curve. So I'm going from 1, 1 to 2, 4. If you go from 1, 1 to 2, 4, change in y over change in x is 3 over 1. So the slope should be 3. And that's what it is right there, is the slope it's kind of a coincidence the tangent line goes through there, but the slope is given by 3 in the red. And as I approach 1, the slope wants to be 2. And again, equivalently, I can do it with y equals x squared, p, fix that 1, 1, and then q, instead of being x comma x squared, like it was before, it's now 1 plus h, and then 1 plus h quantity squared. So whatever the x value is, the y value is that squared. And so now q is just h away from p in the x anyway. So it's another way to look at the same process. The h way is not quite as natural, I don't think, but sometimes it's stressed because then it's easier to go to the derivative of a function that way. The derivative of a function is a little harder when you do the x y way or x f of x way. So this first way I did this, where fix a point and then q is at xx squared. If I want the derivative for general x, it's a little harder to do this way. But if I want the derivative for general x, this is a little bit easier. So this is just x f of x and then x plus h f of x plus h. So you can find the derivative of function. But anyway, so here it is with h's. So this point is h away from p in the x value. So h could be negative, which means I'm to the left. There's h equals 0, which means q is exactly p. Or h can be positive, which means I'm to the right. But either way, you want to let h go to 0. And then you'll approach the tangent. And again, for any function like x squared, it's not too hard to find the general derivative function, 2x. So now I know what the slope of the tangent line will be for every value of x. Like when x is 1, the slope will be 2. But I can get the slope of the tangent line for every x super quick. And plot them all. So for any x, there's the graph. When x is 1, the slope will be 2. And in general, the slope's always double the x value. So the slope's negative for negative x. If x were negative 1, the slope would be negative 2. One more function to look at, the cube root function. So this is not a polynomial, so things are a little bit different, but the idea is the same. So you can either have, for y equals x to the 1/3, fix a point. Now I fix that 1, 1. Q is at the point x, f of x. F of x will be x to the 1/3. And I'm going to let q approach p. Could be to the left, could be to the right, but it's going to approach p. Here's the slope of the secant line. So change in y over change in x. Change in y, x to the 1/3 minus 1 divided by change in x, x minus 1. So again, there's a hole in the graph at x equals 1. Now it's approaching 1/3. It's not too obvious from this graph, but it's going to approach 1/3. And again, if you plug 1 in, you get 0 over 0. So if I look at the secant lines, they look like that. If I want to look at the slope of the secant line. So what's this slope? This slope is 1, because I'm going from -1, -1 to +1, +1. So change in y over change in x is 2 divided by 2. And that's right there. So the slope at x equals -1. If q is at -1, the slope will be 1. And so I've got this slope right there. Now as q gets closer to 1, the slope is approaching 1/3. It's hard to tell, but and so this is an increasing line, but not too steep. 1/3. So here it is again with the tangent line graphed. indeterminate if q is 1, but the limit exists. That's the tangent line. And again, it can be done with, instead of x, f of x, if you fix p, then q can just be 1 plus h, and h could be negative, so you to the left, f of 1 plus h. So you plug 1 plus h into the rule of the function. Again, then more generally, p can be the point x, f of x, and then q is x plus h, f of x plus h. So it's the same process, but now h is how far away we are from the given point p. If h is 0, then q and p are the same point. And again, there's a nice easy way for x to the 1/3. The derivative is going to be 1/3 x to the negative 2/3, or this function. So it'd look like this. And so I can actually get the derivative at every point, the slope of the tangent. So as I change x's, these are all the slopes. This is a little trouble at 0. Go into that. Oops. So the slope at 1 would be 1/3. Anyway. All right, so one last example. The same function, but now p is at the origin, 0, 0, instead of 1, 1. There's going to be a little trouble here. So if I let q approach p, I get, well, then the change in y is x to the 1/3 minus 0, which is just x to the 1/3. The change in x is x minus 0, which is x. So I have x to the 1/3 divided by x. And x to the 1/3 divided by x is 1 over x to the 2/3. So here's x to the 1/3 minus 0 divided by x minus 0. It actually got simplified there. But cube root of x minus 0 over x minus 0. And that blows up. And we can kind of see that happening here. So if I fix p, then as I let q approach the origin, the secant lines get steeper and steeper, and there is no limit. There's no upper bound. You can always get a steeper line for some value of q. So this function is not differentiable at x equals 0. Even though in a way there is a tangent line. Technically in this case, the y-axis is tangent to the curve. But we say the function is not differentiable at x equals 0 because the derivative would be infinite. And we need it to be a real number to say it exists. Same thing as if we do it with h's. So if q is 0 plus h, which is h, f of 0 plus h, which is just h to the 1/3, then everything's kind of the same. So as h goes to 0, there's the plot, so it's not going to be differentiable. In this case, there's no hole that we can fill in. It just blows up. So it's not differentiable at the origin. Again, there's the look at it. So as h goes to 0, there's no limit to how steep the lines can get. All right, so that explains limits and why we need them. We need them for the process of finding derivatives. There's actually a nice way to get the derivative of any function. You can do it with a limit process, but gradually there's actually rules we know, so we don't have to do limits anymore. But we still want to hammer in the idea of picturing tangent lines and how we came to find what their slopes are. Anyway, so that's all I have. Thanks and have a good day.